Good morning friends, welcome to my YouTube channel. So in this channel, as we already know, we have been discussing many topics related to your mathematics NCERT 12th syllabus. In previous session, we were up to the discussion of determinants, right? So we have solved fifth exercise from your NCERT textbook. So today we will start with a new topic, that is application of matrices and determinants. So we are solving matrices, we are solving determinants. So what are the application of them, right? Finally, why do we solve these matrices, right? And why do we solve these determinants, right? So basically there are many applications, out of which the important application is to find out whether the system is consistent or inconsistent. Okay, so to find out whether the system is consistent or inconsistent. What is the consistent system and what is the inconsistent system, right? So the consistent system is the one which is having one or more than one solution, right? That means for any system, if solution is existing, right? So system is, here we speak about system of linear equation or system of simultaneous equations, right? So for the system of simultaneous equation, if there is a solution, then we refer it as a consistent solution, a consistent system. The solution may be one or more than one, that doesn't matter, but solution should exist. If for any simultaneous system solution is existing, then we call it as what? A consistent system. And for if any system, if the solution is not existing, then we call it as what? Inconsistent system. Okay, so based on that we have to decide, right? We have to use the determinants and matrices to check whether the system is consistent or inconsistent. So what is the definition here? As I already explained what is a consistent system, but according to your book, what is the definition here? A system of equation having one or more than one solution. A system of equation having one or more than one solution is termed as what? Consistent system. And what is inconsistent? It's the opposite of consistent. That is a system which is not having any solution. A system which is not having any solution, right? So this is called as what? Consistent and inconsistent systems. Now you can make a note of these definitions. Then I will tell you how to identify whether the system of solution is consistent or inconsistent using the method of matrices. Okay, so make a note of this. So friends, I hope you have understood what is consistent and inconsistent system. Okay, so let's proceed with the matrix method to verify whether the system is consistent or inconsistent. Or let us try to understand how a matrix method provides a platform to check whether the system is consistent or inconsistent. Okay, so for this, what is the thing we have to do is system of linear equation. Solving the system of linear equation by using matrix method. So remember, here we are only focused to check the consistency of linear equations, right? Not non-linear equations. We are only focused about linear equations. Okay, so let us consider the system of equations, right? So a1x plus b1y plus c1z is equal to d1, a2x plus b2y plus c2z is equal to d2, a3x plus b3y plus c3z is equal to d3. Here we are having three set of simultaneous equations. Okay, so from this set of equations, let us assume A is a 3 cross 3 matrix and elements are a1, b1, c1, a2, b2, c2, a3, b3, c3. What are these elements? Coefficients of x, y, z in this solution set, right? In this system of equations, right? So the coefficients of these variables in this system of equations, we have considered that as matrix A, A1, B1, C1, A2, B2, C2 and A3, B3, C3. And let X be another matrix, right? And what are these? These are the variables which we have used here. These are variables which we have used in this system of equations, that is X, Y and Z. And what is B? The constant part, right? The constant part or the RHS part of the system of equation. Let us consider it as matrix B. Here matrix A is a 3 cross 3 matrix. Matrix X and matrix B are 3 cross 1 matrix. Okay, so let us assume this system and let us assume these are the matrices. Then how do we use these matrices how can we use these matrices to represent this system of equation? How can we use these matrices to represent this system of equation? Right? So it can be used in this way. Right? So this given system of equation can be represented using these matrices in this particular way. So this is nothing but another form of this system of equations. Whatever is given here, this is another form of this system of equations. Why? Because if you multiply this, right? If you multiply, then you are going to get back the same set of equations. How? So if you multiply these two matrices, what am I going to get? A1 into x plus b1 into y plus c1 into z. Right? So a1 into x plus b1 into y plus c1 into z. That I will get in the first row. Right? So you can see a1x plus b1y plus c1z. Right? Similarly, second what I will get? a2x plus b2y plus c2z. You can see here the second equation, a2x plus b2y plus c2z. Right? And third one, a3x plus b3y plus c3z. So in the third row of the matrix, what we will get? a3x plus b3y plus c3z. And this will remain as it is, d1, d2, d3. Right? So if we equate both the matrices, once again we are going to get back the same set of equations. Okay? So this is how we need to form the equations. So these matrices can be used to represent this system of equations. Right? So now we have formed the matrices, we have assumed the system of linear equations, we have formed the matrices using them, and also we have used them to represent the same system of linear equations. Now how to find its consistency, right? So there are two cases, we will study them case by case, right? So case 1, if A is a non-singular matrix, if this A is a non-singular matrix, what is the meaning of non-singular matrix? Determinant is not equal to 0. So when determinant is not equal to 0, definitely its inverse exists, right? So we know that very well. So when the determinant of any matrix is not equal to 0, then definitely inverse will exist for that. Okay? So then what is this? This is nothing but representation of A into x is equal to B, right? This is A, this is x, this is B, right? So we'll take up the same thing, Ax is equal to B, right? So multiplying inverse for this, A inverse for this equation, right? I have just considered this equation here, Ax is equal to B, and in the next step I have multiplied A inverse on both sides. If I multiply A inverse on both sides, what do I get here? A inverse into Ax is equal to A inverse into B, right? So A inverse into Ax is equal to A inverse into B. Okay, fine. So I have considered this equation and have multiplied A inverse on both the sides, right? So this is what multiplying A inverse. Now A inverse into Ax can be written as A inverse into A into x. I can group this A inverse and A in the one bracket and x in other side. This is nothing but associative property, right? A inverse into Ax can be written as A inverse into A multiplied by x, and here A inverse into B as it is, right? What is A inverse into A? We know that inverse exists, and A inverse into A is nothing but I, right? So A inverse into A is replaced by I, x as it is, A inverse into B as it is, right? What is I? Identity matrix, its value is 1, we already know. So I into x will be nothing but equal to x. I is what? 1, 1 into x is 1 only, right? So this is x, A inverse into B, right? So here the value of x we are getting. What is the value of x? X, y, z, right? Once we get the value of x, we get the value of x, y, z, right? By this method, what is the inference of this method? Unique solution for the given system of equations can be found out, right? So when solution is found out, that means the system is consistent, right? What was the definition of consistent system? For a system, given system of linear equation, right, solution should exist. When solution is existing, we call it as a consistent system. Okay, so as we have found out the solution here, that means we have verified that, or we have certified that the solution exists and it is a consistent system. And by using this methodology, unique solution will come out, right? So if it is existing, unique solution will definitely come out, right? So why unique solution will come out? Why? Because for any particular matrix, A inverse is unique, right? So for one particular matrix, we don't have two inverses, right? So for one particular matrix, only one inverse will exist. As only one inverse will exist, only one solution will come out with this method, right? So this is how we have to verify whether the system is consistent. When solution is coming out, so that means that the system is consistent, right? So this is about the case 1, right? This is possible only if A is a non-singular matrix. If A is not a non-singular matrix, that is if A is a singular matrix, then you cannot make use of this method, right? You cannot make use of this method. Why? Because if A is a singular matrix, then inverse will not exist, right? Why? Because determinant A will become equal to 0. When determinant A will become equal to 0, the inverse will not exist, right? So we have to go for some other methodology that I will explain in case 2, right? So you will pause this video and take a moment and make a note of this. So friends, I hope you have understood the first case. So let's move on to the next case. Here the basic things I have reproduced, right? What is this? This is a system of equations we have considered, and A, B and C we have framed the matrices out of these systems, and we know that these matrices can be expressed as A into X is equal to B to represent this system of linear equations, right? When AX is equal to B, then what is that? A is here, X is here, B is here. These things can be framed, right? So these are the basic things which I have already explained in the previous slide, right? So now let's move on to the second case. That is, first case was A is a non-singular matrix. So clearly when A is a non-singular matrix, then what happens? Its determinant is not equal to 0. A inverse exists. Directly we can find out the solution. But if it is a singular matrix, right? If A is a singular matrix, then what happens? Determinant is equal to 0. When determinant is equal to 0, you cannot use the inverse method, right? Then we have to go for some alternative method. What is that? So here first step is we should determine adjoint A into B. The first step when it is a singular matrix, we should determine adjoint A into B, right? So after determining adjoint A into B, check whether it is 0 or non-zero, right? So if it is not equal to 0, right? So if the product of adjoint A and B, if it is not equal to 0, then what happens? Solution will not exist. You can see here, solution does not exist, right? So when solution does not exist, what is the type of system we call it as? Inconsistent system. So first condition, if adjoint A into B is not equal to 0, then implies that solution does not exist and given system of linear equation will be inconsistent, right? And second one is, if adjoint A into B is equal to 0, then solution may or may not exist, right? The system may be consistent, may not be consistent, right? If it is consistent, then infinitely many solutions will exist. If it is not consistent, then no solution will exist, right? So in second case, that is if the given matrix is a singular matrix, that is if determinant A is equal to 0, then what is the methodology here? First and foremost thing is determine adjoint A into B, right? When you determine adjoint A into B, check whether that product adjoint A and B, the product of adjoint A into B is equal to 0 or not. If it is not equal to 0, then we can definitely say that the system is inconsistent, right? Keep this in mind. When it is not equal to 0, we can definitely say that the system is inconsistent, right? If it is equal to 0, we cannot comment on the consistency of the system. It may be consistent, it may not be consistent. We cannot comment on that, right? So first one, if it is a non-singular matrix, right, then definitely it is a consistent solution, right? It is a consistent system of equations, right? When it is consistent, definitely when we can say that it is consistent, we can say that the given system of equation is consistent confidently if it is a non-singular matrix, right? And when we can say that the system of equation is inconsistent, we can say it as inconsistent confidently if adjoint A into B is not equal to 0. If adjoint A into B is not equal to 0, straightforward we can say that it is an inconsistent system. If the given matrix is a singular matrix, and if adjoint A into B is equal to 0, then we cannot say anything about the consistency. These are the three conditions, right? So I hope you have understood this one, right? So if at all, if you get any doubt, then you can get me back. So first one was, it is a non-singular matrix, then definitely it is a consistent. If it is a singular matrix, then it may or may not be consistent. How we can say it is not consistent, it is inconsistent if the product of adjoint A into B is not equal to 0. Definitely we can say that it is inconsistent, right? And if the product is equal to 0, then we cannot comment on that. We cannot say whether it is a consistent or inconsistent system, right? So now pause the video and make a note of this, right? So, and don't get confused in this. Go through this clearly. It is very clear and very simple. Don't get confused. So you pause the video and make a note of this, and then we'll solve one or two problems out of this. Then we can end up the session. So okay friends, I hope you have understood that how to identify whether the system is consistent or inconsistent. So let us take up an example and verify that one. Okay. So first example is solve the system of linear equation. What is the system of linear equation? 2x plus 5y is equal to 1 and 3x plus 2y is equal to 1. So this is of the general form a1x plus b1y plus c1z is equal to d1, a2x plus b2y plus c2z is equal to d2, a3x plus b3y plus c3z is equal to d3. That is if the three equations are given. Here only two equations are given. This is also the similar kind, right? So we'll make this one. What was matrix A? The matrix A was coefficients of the elements of matrix A were the coefficients of x and y here, right? So what is given? Given system of equations is 2x plus 5y is equal to 1, 3x plus 2y is equal to 7. This is the given system of linear equation. From this I can form A is equal to the coefficients, that is 2, 5, 3, 2. X as x and y, B as 1 and 7, right? So what was the elements of this matrix? The elements of matrix A were coefficients of x and y in the system of equations given to us that we have written. And what is the element? What are the elements of x matrix? Those were the functions we use. There is x and y. And what is B matrix? There is a matrix including the coefficients. That was the thing we have represented here, right? So two cases will come, right? We know that the two cases will come. In first case, the determinant A will not be equal to 0. That is, the given matrix will be non-singular matrix. In that case, direct Ax is equal to B. We can use Ax is equal to B and we can solve it, right? So how to do that? Okay. So let us find out whether this system of equations will come in case 1 or case 2. That is, whether the matrix is singular or non-singular matrix. If it is non-singular matrix, it will come in case 1. If it is a singular matrix, it will come under case 2. Right? So for that, must and should condition is determinant A. Calculate determinant A. So determinant A is 2, 5, 3, 2. So this is nothing but 2 into 2 is 4, minus 3 into 5 is 15, that is minus 11, and this is not equal to 0. Right? So the given determinant value is not equal to 0, so it is a non-singular matrix, so it will come in case 1. Right? Ax is equal to B is the given case. Right? What is A? 2, 5, 3, 2. What is x, y? This thing, and B is 1, 7. Right? So multiplying A inverse into Ax is equal to A inverse into B, right? So I can form this A inverse into A on one side, X on the other side. That will be A inverse into B. A into A inverse is I, and X as equal to A inverse into B, right? I into X is nothing but X is nothing but A inverse into B. Right? So it is not compulsory to do this thing every time. If you remember, x is equal to A inverse into B, that is more than sufficient to solve this one. Okay. So how to find A inverse? First we need to find adjoint, right? And then we need to go for A inverse. It is a 2 cross 2 matrix. So finding out adjoint is not a difficult task, right? So adjoint A will be directly, you can get it from interchanging the principal diagonal elements and reversing the sign of remaining elements. So this 2 will come here, so this will be 2, this also will be 2. Why? Because both the elements are 2 there. So this becomes minus 5, this becomes minus 3, right? So this is adjoint A, right? Adjoint A is what? Directly by interchanging the principal diagonal elements and reversing the sign of other elements, we get the value of adjoint A, right? So, and what is, how do we calculate A inverse? A inverse is equal to 1 upon determinant A into adjoint A, right? So 1 upon determinant A, that is minus 11, so it is minus 1 upon 11 into adjoint A is how much? 2 minus 5 minus 3 2. Okay, so this is what is our A inverse, right? So A inverse into B, how to get A inverse into B? X is equal to A inverse into B is there. A inverse is what? We have already calculated. Minus 1 upon 11, 2 minus 5 minus 3 2, okay, into B. B is how much? 1 7, right? Okay, so this is how we need to calculate X. So this is minus 1 upon 11 as it is. 2 into 1 is 2. Minus 5 into 7 minus 35, and here 2 into 1, this one minus 3 into 1. See, this is a 2 cross 2 matrix, this is 2 cross 1 matrix, so the resultant matrix will also be 2 cross 1 matrix, right? Minus 3 into 1 minus 3 plus 2 into 7 plus 14, right? So this can be written as minus 1 upon 11, right? 2 minus 35 is minus 33, and minus 3 plus 14 is 11, right? I will write it here. Okay, X what we got? X we got it as minus 1 by 11 minus 33 and 11. So if I take minus 1 by 11 inside, so it will be what? Minus 1 by 11 into minus 33. Minus into minus becomes plus. 33 by 11 is 3, and this will be minus 1, right? So what is this X? X is nothing but xy. So on here itself I can write x y. So x is equal to 3 and y is equal to minus 1, right? So this is how we need to form the equations, right? We can make use of the equation and get the required value. I hope you have understood this one. So we'll stop the session here. Keep trying different problems, as I always say, right? So if you get any doubt, you can get back to me. Okay, so we'll stop the session here. Thank you.